Hi, welcome to another lecture on linear algebra. This is going to be one of the last lectures we are going to have. As you can see, the sun is kind of setting on our course. So we are going to continue our conversation about Eigen analysis of 3 by 3 matrices. And the lecture today is going to be about some of the special cases we might encounter. We are also going to do a bit of a review of how to solve a simple cubic equation. Let's go ahead and see what the story is for today. So, eigenanalysis of 3 by 3 matrices with multiplicity. It means some of the roots are going to occur twice or 3 times. That's going to give us a bit of additional challenge we need to watch out for. Before we actually get to linear algebra, let's do a little bit of a ordinary plain college algebra. The reason for that is that we need to be able to solve cubic equations, and it's good to have a quick review of that. So you know in your algebra class that from high school you come across this quite often. So you know that solution of that comes with an easy formula that has been known to humanity for several thousand years. That's amazing, isn't it? Going 1 degree higher up than this will be so-called cubic equation. X squared plus cx plus say d equal to 0. So that's the case of a cubic, while this one is called quadratic equation. For this one, there is a formula too, but it almost fills the whole page and not going to be very practical for us to use, and it's going to take a couple of lectures itself to derive it. So we are not going to go down that route. We are going to go after simple cases where the roots can be found by guessing, factoring, and so on. So we are going to give up that luxury for a short while and go after some simple cases. So what are the clues we are going to use for dealing with these things? Let me list some basic facts. One is, if I know a root, if if x sub 0 is a root, so somehow you are guessing that say x0 is perhaps is a root, you want to verify. Well, to verify you plug it back here. So being a root means ax0 cubed plus bx0 squared plus cx0 plus d is actually equal to 0. So that's how you verify something is a root. Well, question is, once you have a root, does it help you find other ones? And yes, a big resounding yes to that. The way we do that is by deflation. We say if it is a root, then x minus x0 is a factor, which means whatever polynomial that you have, doesn't have to be cubic, can be anything, it factors to x minus x0 times some polynomial. In this case is going to be quadratic polynomial, some polynomial, which is going to be a degree less than what this one is. This is cubic, that's going to be quadratic, and so that one you can solve it by methods from high school. So if you know a root, you are almost there. Item 2. Well, when you are dealing with the quadratic cases, like when you're dealing with say x cubed plus say 8x plus 15 equal to 0, you say give me two numbers such that the product is 15 and the sum is 8, and so on. Similar idea applies to cubic, except that you're looking at three numbers. So we say if the three roots are x1, x2, x3 are the roots, all the roots are counted by x1, x2, and 3, then the sum of them, x1 plus x2 plus x3, happens to be equal to minus b over a. In that case, it's going to be minus b over a. It's exactly the same thing here. Then product of every two of them, this is going to be perhaps looking unfamiliar to you, but x1 x2 plus x2 x3 plus x3 x1 is going to be the ratio of the next two. This one positive. Let's emphasize that. And just like in this case, you say the product is c over a. In our case, x1, x2, x3, the product of three of them is going to be minus d over a. We are going to do a short example of that, but just keep that in mind. If you have the three roots, you want to verify, or you're searching for them, you have three clues. Item 3, perhaps the biggest gun in our arsenal, is something from college algebra called the rational root theorem. Rational root theorem is a way of going after guessing the roots in an intelligent way. So sometimes you come across, excuse me, I have a mistake here. This was supposed to be quadratic. So sometimes you try to find the roots by guessing it. Well, there are smart ways of guessing the roots as opposed to willy-nilly picking up on a number and seeing if that's a root or not. Rational root theorem gives you a tool to intelligently choose numbers that you're going to try for right fit. It says, suppose a, b, c, d are whole numbers, and it's to your advantage to simplify them, to reduce the amount of work that you're going to do. Then it says, if a rational root exists, what does it mean, rational? It simply means a ratio, like 2/3, 5/7, 9, means 9 over 1, minus 8/15 or something. If a rational root exists, then it is either a plus or minus. So what you do, you list factors of d and divide by factors of a. A factor of, let's write it in a different color, d divided by a factor of a. So it limits the space in which you're searching for the root, trying to guess. You limit how? You limit to list all the factors of this, list all the factors of that, take a ratio of this to that. You only need to search among those. There wouldn't be any rational root anywhere else. Okay, these are the three main tools that we are going to have, and probably the one that you're going to be using most often to start is this one, and then perhaps this is what you're going to use next level. Perhaps sometimes you might make use of this one. Okay, let's go practice in a little problem that we are going to actually encounter shortly. So the problem I'm choosing is related to a problem that we are going to do shortly later. So we are going to so consider the following equation: minus x cubed plus 4x squared minus 5x plus 2 equals 0. Suppose I want to solve a cubic equation. Let me just again remind you, why are we after this thing? 3 by 3 systems are going to come up when you have 3 objects in front of you. So you have 2 objects. If you have 3 interacting objects, then your matrix is going to be 3 by 3, and then you have all of that to deal with. So that is what gives rise to all of these discussions and such. That's why we're doing it. Okay, the question is, how do you solve this kind of a problem you might have seen in your algebra or pre-calculus and so on? Well, our tool number 1, rational root theorem. It tells you if this problem wants to be an easy problem, and all the problems that you're going to see are the easy ones, because the hard ones are going to be truly hard. So if it wants to be an easy problem, then all the roots are going to be whole numbers or rational numbers at worst. All the problems you are going to see, all the answers, all the roots are going to be whole numbers, because in all of those cases this number here is 1. So you have to look for, according to this theorem, factors of this divided by the factors of that. So let me just rewrite this thing on top of the theorem. The equation itself so the equation is like that. The instruction is, look at the factors of D divided by factors of A. Consider all those possibilities, plus or minus. If there wants to be a rational root, it's going to be one of these. In the problems that you are going to have, this one is luckily just 1. So the factors of 1 are just 1, or 1 and minus 1. So you're just left with 2 here. What are the factors of 2? So I write factors of 2. Let me write it in some color. So that's this 2. And this is the 1. Uh, 1 or minus 1. And just consider all possibilities. Well, what are the factors of 2? Factors of 2 are just 1 and 2. What are the factors of 1? Factors of 1 are just 1. So either you have 1 over 1, or it's negative, or 2 over 1, or it's negative. So if this equation wants to be a friendly equation with easy roots, the only easy roots it might have are these. Obviously, it's not going to have all of them, because this has only 3 roots anyway. So some of these things are not good candidates. In more mature problem, perhaps none of them are candidates. So it all depends. You have to try them and see who is an answer, who is not an answer. So we are going to check, is x equal to 1? So it's a question mark. Is that a root? Well, how do I check it? I'll put it back here. So it becomes minus 1 plus 4 minus 5 plus 2. Is that 0? Well, yes, it is 0. So yes, this is an answer. How about x equal to minus 1? So we can try them. We can also, at this stage, once you find the root, you can immediately go into this gear and try to factor your problem and go down that step. It's your choice. Minus 1, is minus 1 a root? Well, it doesn't look like it. Let's try minus 1 cubed. I put it in parentheses that you see, minus 5 times minus 1 plus 2. So this is a question for us. Is that right? This becomes plus 1, plus 4, plus 5, plus 2. Definitely not 0. Everything is positive. You could have told from the alternating sign there that this thing is not going to work. So that, you can draw a red line on that. That didn't work. So some of them do, some of them don't. In the worst scenario, none of them. So x equal to 2. Is that a case? Let's draw. Minus 8 plus 4 times 4, 16, minus 20 plus 2. Well, I made a mistake. 4 times, well, we see that x equals to, I made a mistake here, sorry. Minus 8 plus 16 minus 10, I made a mistake here. 5 times 2 is just 10, and plus 2, and then the total is 18 minus 18 is in fact 0. So this one also is a winner. How about x equal to minus 2? Just like that case, everything becomes positive. That's not going to work. No negative number works, we can tell. Okay, now we are facing an odd situation. I found one root is 1, another root is 2. For a cubic, we expect 3 roots. We always have as many roots as this power. So who is the missing one? We have the third one. Where is that? Several ways of doing it. One is you can make appeal to this one. Product of all 3 of them has to be the minus this divided by that. x1, x2, x3 has to be minus this 2 over minus 1, which is just 2. Well, now I have one answer is 1, one answer is 2. What can I put here so that it'll be 2? Well, of course, the answer is 1. So that means the reason it's hiding is that this is a double root. It shows up twice, and that's the meaning of the word multiplicity here. When something shows up more than once, we have a price to pay. So our roots are 1, 1, and 2. Okay, suppose we wanted to do this problem a slightly different method. I might say, okay, suppose you found one of the roots, x equal to 1. We can use the idea of deflation. If you have a root, you have a factor. If you have a factor, well, then you know the next polynomial, and that one will be easier to solve than the original. So what do I do? So restarting. Suppose all I know is that x equal to 1 is a root. This means x minus 1 is a factor. Factor of what? Factor of the polynomial we had. What was it? Minus x cubed plus 4x squared minus 5x plus 2. Claim is that if you just have this, you have made a big discovery. You can find the other roots easily. How? Here's how. We go ahead and divide, just the favorite activity from your high school class, a long division or short division, synthetic division or whatever, any division is fine. X minus 1. So I take this, divide by that. How do I do it? Take this, divide by that. What's the ratio? I'll write it in red. The ratio is of course minus x squared. Multiplied back, so I get minus x cubed plus x squared. So take minus x squared is minus x squared, multiply by this denominator x minus 1, that's what you get. Then subtract. When you subtract, you are left with 3x squared minus 5x. Continue as before. So 3x squared divided by x, that's going to be plus 3x. Multiply back, so I get 3x squared minus 3x. Subtract, you're left now with what? Minus 2x plus 2. Okay, take this, subtract this from it, that's what you get. Now what? For last time, take this, divide by x, and you get what? You get minus 2. Let me write it in the same color. So minus 2. When you multiply, you better get remainder of 0. Otherwise, you are mistaken into thinking that this is a factor, or you have made some other mistake somewhere else. So if everything worked out, remainder will be 0. So that is always has to be remainder, has to be 0. Otherwise, you better stop and double check everything. So what does this mean? It means if you had minus x cubed plus 4x squared minus 5x plus 2, you could have factored it to x minus 1, and this is the quotient, minus x squared plus 3x minus 2. Let me go ahead and factor a minus out of this so it looks more familiar to you. Oh, sorry. So I put the minus out here, x minus 1. Now this has a factorization. You have seen this in high school, I would say 100 times. X minus 1 times x minus 2. You see the multiplicity? It shows up twice. Okay, if you set this thing equal to 0, you get x equal to 1. Okay, you count how many times it has happened with multiplicity 2, meaning 1, 2 has happened twice. How about x equal to 1? Well, that's a single. Just like when you're playing cards, you say I have a double, or I have a pair, or something like that. Here, same language. 2 multiplicity is 1. Now, if you remember a lecture a while back, we said we have two notions of multiplicity. One is the one that shows up here, that's called algebraic multiplicity. Algebraic multiplicity means when you're factoring this polynomial, you suddenly go to 0, find the roots, you count how many times certain root shows up, what you get there. That concept of multiplicity is called algebraic multiplicity. Later on, when you go to count how many eigenvectors you got, eigenvector has some sort of a geometric connotation to it, and that one, depending on how many of them you find, you call it geometric multiplicity. Geometric multiplicity is at most equal to algebraic multiplicity, and at least it's equal to 1. So we are going to go toward another concept that's going to come up later, geometric multiplicity. That is how many linearly independent eigenvectors tie in to a particular eigenvalue. That's called geometric multiplicity. It is at most whatever you have here as algebraic multiplicity, and at least it is 1. So for example, if this is geometric, algebraic is 1, geometric is also forced to be 1 because it has to be between 1 and 1. But if this algebraic multiplicity is 2, geometric could be 1, could be 2. Okay, so we are getting a little bit of a detail here which we didn't have before. Just be patient. We are gonna be done with this thing quickly. So we are now hopefully ready for handling the big topic. So pretty much everything we said so far, how to find the roots, the review of college algebra. Hopefully you had a good college algebra class where you went through all these things. But even if you didn't, here's the way to fix whatever you were missing there before. You might as well pick a college algebra book or pre-calculus book and read the section on finding roots of polynomials. You will see lots of facts like this and even more. Okay, now the question is, what do we do with all of this? Well, we are going to start from scratch essentially. We have a matrix. In this case, our matrix is, let me see, 0, 1, 0, 0, 0, 1, 2, minus 3, no, 2, minus 5, and then 4. So our question is find eigenvalues, eigenvectors, eigenspaces of M. Step 1. Set determinant of M minus lambda equal to 0. So M minus lambda, we say lambda is subtracted from the diagonals to now be my guest to figure this determinant any number of ways you had. You can expand on this row, you can expand on this column, you can do that so-called shortcut. Whatever is your choice, that is fine. So perhaps I do expansion on the first row, so I'll have minus lambda times determinant of whatever is left, determinant of minus lambda 1 minus 4 minus lambda. The next number, you remember we have to associate this thing with a checkerboard sign. So next one is going to attach to a minus, so it's going to be minus 1 times the determinant of whatever is left, which is 0, 1. So remember how we go about this thing. We take this column and row out. See what is left, 0, 1, 2, 4 minus lambda. And then third time, I have a 0 times determinant of whatever is left, but I don't even care what is left because multiplying by 0. So this portion is going to be 0. Now I have minus lambda times product of these two is a lambda squared minus 4 lambda. Product of these two times a minus becomes plus 5 minus product of these two is 0. Product of these two and a minus becomes minus 2. So multiplying again, minus lambda cubed plus 4 lambda squared minus 5 lambda and then plus 2 equal to 0. Does that look familiar? Or there's lambda over here is x. It's the same thing, is that right? So at that stage, if your cubic is didn't give you any kind of other clues as to what the roots are, unlike the previous problem that it was immediate as to what the roots are. In this case, the roots, you have to go through all these steps to find the roots of 1, 1, and 2. So here, follow the steps above to get lambda is either 1 or it's 1 or 2. So this might be listed as lambda 1 is equal to 1, lambda 2 is equal to 1, lambda 3 is equal to 2. These are going to be called roots of multiplicity 2. And this type of multiplicity is going to be called algebraic. Okay, next up, we have to go find eigenvectors. Okay, eigenvectors for the eigenvalues that are single, that their algebraic multiplicity, this one is algebraic multiplicity 1. That's going to be straightforward. It's going to be exactly what we did in the example we had last time. So if I go ahead and apply lambda equal to 2, let's go after that one first. That's going to be easy. Lambda 3 equal to 2. I go ahead, plug it here. So it's going to be minus 2, 1, 0, 0, minus 2, 1, 2, minus 5, and then 2. I want to find the null vectors of that. That's going to be the eigenvectors of the original matrix M. So we take our lambda, put it here, find the null vectors of that. And whatever we find is going to be part of so-called the null space of this. Now, how do we do that? Again, you have a choice of doing this thing by hand or doing it by the calculator we provided for you. And in this case, let's just go and quickly do it on that calculator. Minus 2, 1, 0, 0, minus 2, 1, 2, minus 5, 2. Double check, make sure I don't have any incorrect entries. Okay, so we go to, where was it? Edit. So this is minus 2, 1, 0, 0, minus 2, 1, 2, minus 5, and 2 again. Is that right? Double check. So hopefully you guys are going to do this thing by yourself instead of waiting for me. So let's go standard way. I make this thing 1. I use that as a pivot to erase this. Okay, now I make this one into a 1. Use that to erase the one below it. And here's a good sign that this all turns into zeros. That means we are on the right track. The rest of it we are going to continue on paper. We are well, we might as well, you can change this, or you can let's do that. Okay, so now we have it in the so-called row reduced echelon form. That's as clean as it can be, so we always go down to that level. we have ones and then some other numbers. Then we go to paper. So our problem now became the following. The last equation just 0, 1, 0 minus a quarter, and the second equation is 0, 1 minus a half. X, y, z is equal to 0. And the last row was all zeros. So first equation reads like x minus a quarter of z is equal to 0. Second equation reads y minus a half of z is equal to 0. Last equation just reads 0 is equal to 0. That is what allows you to take z, call it a parameter, then your y, you take this thing to the other side, becomes 1/2 of t, and your x becomes a quarter of t. So x, y, z, factoring a t, becomes 1/4, 1/2, and 1. Now to make life easy on ourselves, we take t to be a friendly number to clean all the denominators. T can be anything other than 0. They are all acceptable. So here are several ways of answering this. Eigenvector for lambda 3 is equal to 2. Eigenvector, we might call it v3 to match with that. Any multiple of this will do. We said take t equal to 4 so that life will be a bit easier. It comes 1, 2, 4. Eigenspace. Several ways of writing it. One is just this multiple. Another one is just any multiple of this one. It doesn't matter which one of them you pick for all values of t. Or another style of referring to this thing, span of that. How do we verify this is an answer? We take the original matrix multiplied by v3 we found. It has to be doubling. So I'm going to leave that to you so that the lecture doesn't become too long. This check to see if it is actually true. Okay, so far is exactly like you had in the previous lecture. Graphing of this thing also a very similar situation. So you say 1 step and 2 steps and 4 steps, and that would be my eigenvector, and the line that goes through all the thing, that's going to be eigenspace. So that's the eigenspace is this one. What is new is what to make of the fact that lambda 1 and lambda 2 are the same numbers. Well, what about it? What about it is that when we go ahead and put it in this matrix, so I have the matrix over there, minus lambda 1, 0, 0, minus lambda 1, 2, minus 4, 5, 4 minus lambda. So let me rewrite it down here for you. Oh, sorry. So my m minus lambda was minus lambda 1, 0, 0 minus lambda 1, 2 minus 5, 4 minus lambda. Put the lambda equal to 1 in it. I get minus 1, 1, 0, 0 minus 1, 1 again, 2 minus 5, and this one becomes 3. Is that right? Now, what we are solving is null vector of this. What should I multiply this thing with to get 0? So let's go to our lifesaver there. Let me write this thing on a paper so that I don't flip-flop so much. 2 minus 5, 3. . Where were we? Yes, here. Let's do a reset, edit, start again. -1 1 0 0 -1 1 2 -5 3. Okay, resume, standardize by dividing by that, take this, target that, make this into a 1 by dividing by itself, use this as a pivot. You can use this to erase the one above it as well. So what we got is very clean: 1 0 -1 0 1 -1, and then last row is all zeros. So go back to paper. So the equation we have boiled down to the following: 1 0 -1 0 1 -1 0 0 0 x y z equals 0 0 0. So first equation really reads x minus z is equal to equal to 0. Second one, y minus z equal to 0. And the last equation, well, it's just saying 0 is equal to 0. So we have freedom. Somebody can go free. Here's our style. Last one, z, start with that. Here it's all clean. Everything is just equal to t. So x, y, z is equal to t times 1, 1, 1. So our eigenvector v2, you want to call it v2, you want to call it v1. When you're going on web assign, pay attention to the notation. v1 or v2 is just 1, 1, 1. There is only one eigenvector that is shared between the two of them. Okay, now since we find only one eigenvector, we call this thing to have a geometric multiplicity. To be 1. If we had found two solutions, if there were 2 degrees of freedom here, there was a t and an s. We are going to do that maybe in the next lecture. Then you say the geometric multiplicity is 2. But right now we have only one type of eigenvectors, and that's it. Because geometric multiplicity fell short of the algebraic multiplicity, the matrix is called defective. Something is not quite right with it. It doesn't have all the eigenvectors we expect it to have, and the matrix is called defective. The original matrix, sometimes M is defective, or some terminology like that. So that happened because the geometric multiplicity turned out to be less than the algebraic multiplicity somewhere, and we were short of eigenvectors. And then what this causes is that our diagonalization idea is not going to work the way we expected. So there is some headache down the road in that direction. Okay, so that is how to solve one case of matrices with multiplicity. Maybe we'll have another example, but let's put that on a separate lecture. Okay, until next lecture, good luck and God bless.